familiar at our university. Mark is here in the context of a research project that we have, which is funded by Innoviris, Brussels regional science agency. And so the project is running now for 6 or 7 months or so. And during the review of the project, we were asked to spend to devote some time and effort and money to security. And then how did we get to meet Mark? I think through Peter, indirectly in 2004 he was here at Jordan, I think. So I think that's when we met Mark.
I don't know,
at first.
2004.
Yeah. And at that time you were still working on your E programming language. And we were also doing stuff in security on a programming language level. And I guess that from an industry point of view, at that point, no one was really interested in security of programming languages. But I guess now it's a very relevant topic, especially with all these languages running on your devices in your pocket. So we have given Mark sort of a carte blanche to give us an industry-oriented topic, but of course we are a university. So Mark, off you go.
Okay, I'm going to tell you today about how to do secure distributed programming using object capability security in modern JavaScript. And I'll explain what these terms mean. So I'm going to start the talk by explaining what object capability security is and why you should want it. Then I'll explain how to use JavaScript as a local object capability language. How to extend from there to support flexible and secure mobile code in JavaScript. Then, beyond mobile code, how to extend onto the network to message to remote objects and still keep the virtues of the security model you're about to see as we extend onto the network by using cryptography. And then I'll bring all of these elements together to paint the picture of uniform, secure, distributed computing. So, on this slide, I'm presenting a complete history of computer security, a very brief one. From the dawn of time in the 60s, there have been two fundamental access control models. Identity-based access control, what has come to be known as access control lists, in which all security questions start with the question, who is making this request? And whatever identity is presented as the result of that answer, the identity associated with the request, the decision about whether the request should be allowed is made on that basis. The other paradigm, also originating at the dawn of time, is what was known as capabilities, what is now known as object capabilities. And for that one, all security questions begin with the question, is this request authorized? And if the request is authorized, then you can allow it to proceed, and you don't need to know or care who is making the request. So a question like that doesn't even need to have a coherent answer. You don't need a global coherent theory of identity in order to proceed with security. In the 1970s, decades before the rise of malware, the industry, as it was growing, effectively faced a choice, a fork in the road, and through various accidents of history, it chose the ACL path, the ACL fork in the road. And then in the 90s, we started to see the real rise of malware, and the security situation has gotten worse ever since. Overall, the history of the computer industry and of computer science is this glorious history. Things keep getting better and better and better. Except for security. We seem to be stuck. And in fact, if you look at the statistics, in many ways, things keep getting worse. So the only perspective from which things are continuing to get better in computer security is from the perspective of the attacker. So what's the problem? Why is it that despite such glorious progress on all of the dimensions, we can't progress on computer security. Well, the problem you see is that there's this program. There's this very powerful program. There's this program that's so powerful that it can scan through all of your files to find your secrets and sell them on eBay to the highest bidder. It's so powerful that it can delete all of your files. What is this very powerful program? Well, this powerful program is Solitaire, and it's every application you install on a conventional operating system. Solitaire, the only authority that it needs is to be able to render to the user and receive user interface events. The only thing it's doing is interacting with the user. However, our current operating systems, by design, give it the authority to delete all of your files. Why is that? It's because of identity-centric access control. When Solitaire would try to delete your file, the operating system asks, well, who is making the request? By the theory of identity that the operating systems are built to, the answer is you are making the request. Solitaire runs as you, and because, so then the operating system says, okay, well, do you have the authority to delete your files? Well, the result is that Solitaire can delete any file you can delete. To escape from this problem of installed applications, people turned to web applications. So now let's do a very brief history of the web. This is what the original web looked like. All web applications ran only on the server side, and browsers just displayed HTML data as pure data. So the interactivity was that when a user clicks on a form or a form button or a link, the browser sends an HTTP GET or POST to the server. The servers often ran as event loops, would process a single event at a time, and then return a new HTML page for the browser to render. The Ajax revolution was really the revolution of safe mobile code as protocol. The server, in addition to returning HTML to tell the browser what to render, would also return, embedded in that HTML, JavaScript to tell the browser how to interact with the user. Now that we had JavaScript running in the browser as well, the JavaScript in the browser could also directly issue HTTP GETs and POSTs to the server, independent of user action. To deal with the security issues that arose, the browsers instituted this bizarre security model called the same origin policy. And we see the meaning of it on the slide. It's the policy that attempts to enforce the restriction that JavaScript at a given page or frame can only speak back to its server of origin. Separately, servers found they could impersonate browsers to other servers by issuing HTTP GETs and POSTs, and in so doing, do the server-to-server composition of web services. Programmers' needs to speak along the other pathways on this picture was so great that they found various holes in the browser security model and made use of them to speak on these other pathways. This abuse of those holes was so valuable that the existence of those holes became entrenched, and nobody can any longer fix them. The primary hole, JSONP over here, is yet another form of mobile code as protocol, this time with really terrible security problems. Modern web standards provide better engineered alternatives to those kludges. And the result is that because we evolved here gradually and by overcoming the limitations of the original designed architecture, the result is that these different pathways have different APIs, seem like different technologies, but really the end result is a uniform symmetric picture of objects in event loops sending asynchronous messages to be processed by objects in other events. If we could only abstract over all these annoying differences, we could program to this uniform symmetric model, and if we can shift our focus of attention from the event loops to the objects, then we would also consider these channels for communicating between the event loops to just be a transport over which multiple object references are multiplexed, and where the object references remotely, as with locally, carry, carry messages, code, objects, and references. Okay. So once we build up to this picture, then one of the main benefits for thinking about your distributed system is that for many purposes of analysis, not for all purposes, you can focus just on the internet as a big distributed heap of objects, a big distributed object graph. And you change your focus from thinking about the machines and the machine boundaries and the process boundaries to the objects and their relationships to other objects. However, there's a problem. There's a problem with web security as it exists right now as a foundation onto which to build this powerful model. And the problem is that there's this very powerful email message. Right now, many web applications are web applications that convey third-party content. An example of this is if I send you an email message, I can send you an HTML email message, I can send you an email message that has embedded JPEG images or whatever, and the email systems will convey the content of that message, including the rich text, the markup, and the images through the email system, present them to the web-based email, let's say web-based email is what I'm talking about here, and present them in your web-based email interface. However, if the HTML that I'm sending is HTML that contains a script, over here is a perfectly innocent script. What it's doing is, this is the markup content of the email, the data content, is just this particular phrase. And this little script is just something that the author of this phrase wanted to do to enhance the experience of the reader. All it does is it animates the phrase and provides a little bit of interactivity. But every web-based email system in the world will strip out the script and only present the data, leaving the data dead. All the interactivity is gone. Similar, it's not just webmail, it's blogs and wikis and 1,000 other web applications will do this. Well, this is a bizarre result because the AJAX revolution was the revolution of safe mobile code as protocol. If JavaScript is safe mobile code, then why is it that you can't send me JavaScript and I can experience the interactivity that you were authoring with that JavaScript? Well, the reason is, again, identity-centric access control. The browsers made the same mistake that the desktop operating systems made, but they made it in a narrower way, but still the same mistake. If your web-based email system did not strip out this script, then when the script ran within your email interface, your web-based email interface, it would run as you at that email provider. That's better than running simply as you and being able to do everything you can do. It can no longer manipulate your Facebook account or whatever. But everything that you can do as your account with your email provider, if this script were not stripped out, it could also do, and that includes deleting all of your email messages. So the other virtue of our web situation is that at least the web applications facing this problem fail safe rather than unsafe. But they do strip out these scripts, so we don't have the insecurity problem. Instead, we have the tragic loss of an opportunity. We've got these systems convey media, rich media to the user. But code is the most general form of media. It's the only form of media that has an open-ended set of possibilities of how it might interact with the user. the overall picture is that back in the 70s, the computer industry made a choice before they knew what the search space looked like. Having made the choice, we're now in the maze down here in the search space. We keep searching for some way to organize computation such that we end up meeting the goal of convenient, expressive, flexible, and secure computation. And we keep searching the maze and we keep not making progress. And one of the things we know from the computer science of search algorithms is if you make a speculative choice and then you start exploring the search space that descends from that part of the speculative choice and you're not making progress to the goal, you should at least consider the possibility that you're stuck in a cul-de-sac. You should at least consider the possibility that the thing that you should do is backtrack up to the previous choice point and explore the other part of the search space. It might still not lead to an answer, but the one thing we should be confident of after spending $1 trillion is that it's at least hard, if not impossible, to find an answer just moving forward from where we are. Okay? There's a problem, though, which is we have spent well over $1 trillion building up the computer security industry. We really don't have the option of just saying, well, it was built on the wrong premise, let's throw the whole thing out and start over. Okay? So, it seems like we're stuck. We can't go forward and we can't go back. What can we do? Well, go sideways. What we need to do is we need to find a tunnel that takes us back onto the other path. It takes us to the logic of how we would have constructed things on the other path while preserving the investment in building up the computer industry that we've got. And this seems like a hard thing, but it turns out we're in luck. For reasons having nothing to do with security, there's been this revolution for decades now in the world of software, which is object-oriented programming. Object-oriented programming has arisen for purposes of supporting abstraction, modularity, composition, reuse, flexibility, and the logic of object-oriented programming for these other purposes turns out to very closely resemble the logic of security that was built on that other path. And this is not simply a lucky coincidence. There's actually a deep reason for this. The reason is that the capability paradigm from the beginning saw security and modularity as a line, as not as separate concerns. It saw security as simply the extreme form of modularity. What does this mean? Well, what does modularity mean? It means that modules, components, are as loosely coupled as possible while still being able to interact the way they need to. It means that needless dependencies between these components, we avoid them, and they're dependent on each other only to the extent that they need to be to accomplish what they're trying to accomplish. Security is to design frameworks of interaction such that the components interacting with each other can attempt to interact cooperatively, but where each is not needlessly vulnerable to the other. They can attempt to cooperate while generally being safe from the possibility of the other one's misbehavior. Vulnerability is a form of dependency. If I'm vulnerable to you, then my correct operation depends on your lack of malice. So in computer security done right, anything that decreases vulnerability decreases dependency and increases modularity, and that's what we've seen in practice. The main tool we have for building more modular systems is the principle of information hiding, going back to David Parnas in the 70s. And that's the principle that you should build the interfaces of components such that they hide as much implementation detail as possible, and both release to their customers, to the clients of the interface, and demand from their customers only the information needed in order for the component to realize, to do its legitimate duties. In security, the main tool we have in our tool belt is the principle of least authority. The idea that a component, that the interface to a component should be designed so that it releases to its customers and demands from its customers only the minimum authority needed for the component to do its job. That the authority is only provided on a need-to-do basis. So, if we're going to rebuild computer security starting from objects, we need to understand objects. Here's the central important fact about objects from our point of view, which is the points-to relationship. The points-to relationship is the foundation of object-oriented programming. Objects point at each other. And some objects don't point at certain other objects. In the initial conditions of this diagram, Bob does not point at Carol. Alice, Bob, and Carol are 3 objects. If Alice, who does point at Bob and does point at Carol, invokes Bob's foo method, says Bob.foo Carol, she's passing to Bob a copy of her pointer to Carol. And Bob, as a result of receiving the message, now has a pointer to Carol. And in objects, if you have a pointer to some other object, you can use that other object's public interface. Now that Bob has a pointer to Carol, he can make use of that Carol's public interface. So many programming languages, like Java, for example, have real memory safety. Pointers are unforgeable. If nobody gives you the pointer to Carol, you can't just make it up out of thin air by casting an integer. And have real encapsulation. If you have a pointer to Carol, you can use the public interface, but you can't reach inside and grab private instance variables. To this constraint, we need only add 2 more constraints to turn objects into object capabilities. That an object should only be able to cause effects on the world outside of itself by using references that it holds, and that an object should be given no powerful references by default. As a result, each individual object comes into existence naturally sandboxed. It comes into existence without any possibility of causing effects outside of itself other than those explicitly granted to it by other objects passing it references. Okay. So the only reason I qualified this with powerful is that a very common kind of object in object-oriented programming is the transitively immutable object. The object that is completely stateless, that does not lead to I/O devices and does not have any state that can be assigned to. So these things, so purely functional programming is an example where you have only purely functional data. But much good object-oriented programming has large numbers of individual objects and trees of objects that are internally purely functional. Because a pointer to a purely functional object does not enable the causing of any effects, of a transitively immutable object, does not enable the causing of any effects, it's okay if objects are born with implicit references, with ungranted references to purely immutable objects. And the techniques that you'll see later in the talk for securing JavaScript take advantage of that possibility. Okay. With these 3 constraints taken together, we get the following 4 benefits. The reference graph, familiar from the object programming literature, becomes identical to the access graph from the access control literature. We have this wonderful graph connectivity property that we refer to as only connectivity begets connectivity. This is best understood by example. So for example, if you have 2 isolated subgraphs, they remain forever isolated because no object can ever be in a position to introduce them. This is the reason why garbage collection is generally unobservable. More interestingly, if you have 2 almost isolated subgraphs, then they can only interact or become further connected according to the decisions of the objects that have a foot in both. And therefore, those are the positions in the graph topology that are the strategic locations to place the objects whose behavior expresses security policy. We'll see an example of that shortly. It leads to the natural expression of least authority, because now this principle simply means that when you design the interface of an abstraction, the interface should not require the provision of parameters that are not required for the legitimate duties of the abstraction that it's an interface to. And that's just sane interface design anyway. And most important, it enables us to use the expressiveness of object-oriented programming, to apply that expressiveness to the problem of expressing security patterns. And by bringing that power, that expressiveness that we've built up for all sorts of other reasons, we enable ourselves to express the solution of security problems normally thought hard with simple, elegant pieces of code. Okay. On this slide, I'm going to teach you all the JavaScript you need to know to follow the remainder of this talk. JavaScript, for all of its irregularities, is actually built on a very beautiful, simple core set of ideas. There's really two fundamental abstractions in JavaScript, neither of which is the classic object from object-oriented programming. I'll call these two abstractions the function and the record. So make counter is a function, and every time it's called, it creates a count variable, initializes it to 0, and it creates and returns the record that begins from this open curly and ends at this closed curly. And this is a record with two fields named inker and decker. The values of those two fields are the functions that these function expressions evaluate to, so the value of the inker field, for example, is a function that when called will increment the count variable and return the resultant value.
So what you're saying is make counter is a class and it returns objects when you call it.
Yes.
Basically.
That's right. That's right. So what Peter said is that this pattern of composing functions and records gives us the classic, the equivalent of the classic object from object-oriented programming. So you can just think of this pattern as how you express classic objects in JavaScript. A record of closures hiding state, the state being the count variable. Closures are just a fancy name for the functions that these function expressions evaluate to. So a record of closures hiding state is a fine representation of an object of methods hiding instance variables. The object being returned, which is this record, the inker and decker is effectively the methods of that object, and count is the instance variable of that object. Throughout the talk, I'll be using the following graphical notation for our objects. In this graphical notation, lexical scoping is represented as spatial nesting. So make counter is scoped throughout this body of code. And the multiplicity of layers reflects multiple instantiation. Every time make counter is called, it creates a new triple of a count variable, an inker method, and a decker method, where the inker method and decker method both share access to the count variable. The inker and decker methods are shown touching the edge of the layer because they're potentially accessible outside the layer. The count variable is shown internal to the layer because it's encapsulated. It can't escape. The only things that can possibly get access to it, as we can tell by simple inspection of the code, are these inker and decker methods. So if this pattern simply had the properties that I just explained, it would be a wonderful starting point for security. However, when we started in on this mission, the current JavaScript is the JavaScript standard known as EcmaScript 3, and it's the one that we've had on all the browsers for most of the last 10 years, until very recently. So we started doing this in EcmaScript 3. We built a translator from the secure subset of JavaScript into EcmaScript 3. It turned out to be much harder than we thought because of essentially of these three problems, which is EcmaScript 3 was not statically scoped. The scoping was this crazy confusion of static scoping concepts and some dynamic scoping concepts, and some structural concepts. Even aside from the scoping problems, it had other encapsulation. The functions weren't truly encapsulated. If the functions don't encapsulate the Kent variable, you don't have a starting point for security. And your records were pervasively mutable. There's nothing you could do in returning such a record to your users. If two mutually suspicious objects were sharing the same counter, either one could replace the anchor method with some other method, such that when the other client then goes to invoke the anchor method, he's really invoking the malicious anchor method installed by the attacker. So we took the lessons from we succeeded at securing EcmaScript 3 by the translator. It was very difficult. We took the lessons from why it was difficult to the EcmaScript committee, helping with the design of EcmaScript 5. And as a result, EcmaScript 5 becomes a very easy to secure language. In fact, an almost trivial to secure language. And when I say to secure, EcmaScript 5 itself is not a secure language, not an object capability language. However, this trivial securing that I'll be explaining allows us to build on EcmaScript 5 what we're calling secure EcmaScript, or SES. So in SES, and in EcmaScript 5 itself, this useScript directive repairs any code that's within a useScript directive. So by just putting that at the top of your program, you've repaired all the scoping problems. You now have genuine lexical scoping. And you've also repaired all the additional encapsulation links besides the scoping links. So you've repaired all of that. And then this def here is an SES abstraction over the primitive called object.freeze in EcmaScript 5 that allows you to make this record tamper-proof. So the clients of the record can read and invoke its methods, but they can't change what the methods of the object are.
Is that runtime compiled?
So in JavaScript, the question was, is that at runtime or at compile time? And in JavaScript, the answer to most such questions, independent of subject matter, is at runtime. But specifically, the scoping repair and the encapsulation repair, that's static. The freezing, the making of tamper-proof, that's dynamic. Okay. Afraid of that. So I don't have internet access. I cannot refresh this page, and therefore I'm only going to refer to a static picture of the interactivity you would have seen. I was prepared for this possibility. So over here we have a blog-like application that we've written using the elements that you've seen. That we've written in Caja. It's called Caja, the Caja corpora. The Caja project is a project that includes the old translator that I was explaining. It includes SES, but it also includes elements for securing and virtualizing the HTML DOM and CSS and all the many of the other elements of web media. You need an integrated solution across all of them. But I'll only be speaking today about the language issues. This blog-like application is one in which you can post little comments. And like with many blogs, you can express your comments in HTML. So this is the form in which you enter your comments, and each of these comments above here is a comment that had been entered by somebody through that form. Yes?
Could you give the intuition, how do you implement def?
So the important starting point is that EcmaScript 5 has built into it a new primitive called object.freeze. So for purposes of this talk, wherever you see def, if you simply wrote a direct call to object.freeze, these objects would have enough integrity to sustain everything I'm talking about in this talk. The additional functionality that def provides over object.freeze is it freezes the objects deeper than just the top-level object. Object.freeze is a shallow freeze. Def is a transitive cross property and prototype traversal, and since I don't need to explain what that means in this talk, I'm going to postpone that. Okay. So, unlike other blogs, you can include HTML in your JavaScript, and the result is that these comments are interactive. They can animate, they can interact with the user. If I was able to show you the live demo, I would show you that. And over here, I'm taking the contents of our previous bit of active content, the animating text, and I hit accept, and here it is, hello programmable world, and it animates, and it reverses direction when you click on it. This over here is a little bouncy ball that interacts with the cursor. So the point here is that imposing the object capability restrictions on the code that was accepted is in some sense a form of sanitization. It's analogous to the sanitization that existing blogs and wikis, etc., do, except that they don't, the price of sanitizing the patient is no longer to kill the patient and leave a dead corpse. The legitimate activities of the sanitized code, which is determined by the containing application, according to what references it provides, those legitimate activities are preserved while illegitimate activities are prevented. And they're prevented simply by not providing the authority needed for those forms of abuse. Okay. So, if all you're concerned about is the language part, not the HTML and CSS, etc., you can turn a web page into an SES page, a secure EcmaScript page, simply by loading this particular script first, putting this script tag at the top of your page. It will initialize the page, use EcmaScript 5 on itself essentially to secure it and constrain it to object capabilities.
So this will work. Nothing can interfere with that loading in the beginning. Change the file to something else.
That's why I said you put this at the beginning of your page. You have to
You
run
put
this.
it in.
You have,
So
yeah.
you're responsible. So this is the user. This is
Okay.
the only weak point.
So no. So keep in mind the example that you just saw, okay? Which is where the web application, the enclosing web application, which is the Caja port, puts this at the top of its page, and now it can safely load third-party content and present it to the user without needing to trust that content. So you've enabled code to be treated as media. With regard to the containing page itself, that single non-compositional first level of security, the existing browser sandbox has already dealt with securing that. Otherwise, we wouldn't be able to use the web at all. What's going on here is that first level of security was done in a non-compositional manner because it relied on this finer-grained notion of identity. The same origin policy said you've got one more level of isolation that you didn't have on your desktop because we've made one step finer a notion of identity, which is it's no longer you, it's you at this site versus you at that site. By shifting paradigms completely, we didn't add just one more level. We've added as many levels as you want. This third-party content can load fourth-party content. It can be composed of fourth-party content without threatening the third party.
None of the parties that are involved later can do something to remove
That's right.
security.
If they could, then this whole story would be very silly. Okay? So as a matter of fact, when you throw this out as a challenge, please try.
Okay.
Okay. Yes?
Isn't it just possible to remove the script with the DOM deletion and the part where you put your URL?
So no, and it's a perfect segue for what I'm about to explain. I'm about to explain what it is that init SES does. I'm not going to explain all 7 steps here because of time limits. I'm only going to explain the part with the bullet, and of that, only the eval. So JavaScript has a built-in evaluator that evaluates the source code for an expression, evaluates it as an expression, and provides you the resulting value. We take that primitive eval and we replace it as part of the init SES initialization. And our replacement for eval enforces only 2 restrictions in addition to the page-wide restrictions that the other initialization steps have already done. The additional restriction that the eval imposes is that all of the code that it evaluates is constrained only to strict mode and therefore to lexical scoping. And having constrained it to lexical scoping, it also ensures that the script does not address any global variables that are not on our whitelist. And with regard to what is on our whitelist, now we go to the question that you asked earlier, which is objects that we have made transitively immutable and therefore harmless, like object, array, map, JSON. You go ahead and put those objects, sort of the built-in language primitives, and make all of those on the whitelist so they can be addressed by the code being evaluated. But the objects that enable effects, like window, document, the XML and HTTP request object that enables communication on the network, none of those are on our whitelist. The containing page can still provide those, if it wishes, to the application when running, or it can provide a virtualization of that. It can run the script in a scope where when it says window, it doesn't mean the real window, and this is in fact what the Caja core does. When this application says window or document, it's not getting the real window or document, because this is all just one page, there's no iframes here. It's not giving the real window document. We're taking our virtualization of the DOM has taken a subtree, has enabled the containing application to take a subtree of that DOM and say, present access to this subtree as a virtual window and document. So this guy can render and interact with that subtree, but he can't climb out of that subtree. And he can't threaten the other comments that are in this block. Okay.
But can you like play with CSS to, for instance, to sort of fishing?
So first of all, with regard to the DOM virtualization and the securing of CSS and the securing of HTML, all of this you need a lot more than the init SES script. I'll refer you to the Caja page. Caja is a completely open source project, by the way. It's on code.google. Caja is spelled C-A-J-A. So with regard to CSS, we rewrite all of the CSS in order to basically a set of renaming tricks. And the way to think about our DOM virtualization and our CSS virtualization is to think of it as analogous to what memory management unit, MMU, does in the CPU, mapping virtual addresses to physical addresses. The applications running in MMU address memory just as if they were addressing virtual addresses, but what it's doing is it's doing a name remapping. So when it says one name, it's mapped to a different name on the underlying system. So mapping the DOM access into access to a subtree of the DOM, mapping the CSS style names into style names that are local to the individual component, we're doing all of that. And as far as we know, we're doing it successfully. We've deployed at scale, in particular by Yahoo, and it all just seems to work. Okay, so let's explore the implications of securing eval in this manner. If Alice brings in Bob, which is some third-party content from some site she doesn't trust, site B, she brings in the source code of Bob, and she brings in the source code of Carol from some other site, and she evaluates them with her safe evaluator, then Bob evaluates into some subgraph of objects that only Bob's author knows. It's just the subgraph according to whatever Bob's code is. And the root of that subgraph, the value of the expression that Bob evaluates to, that's returned to Alice, who stores into this Bob. So at this point, ignoring the transitively mutable objects, Bob has no outward pointers. Bob can cause 0 effects on the world outside of himself at this moment. And likewise for Carol. In fact, the only connectivity that Bob has to the rest of the graph is that Carol points at him. He doesn't have any pointers outward. So at this moment, Bob and Carol are confined, and Alice is in complete control over how they might interact or get further connected. What can Alice do from this powerful position? Let's move Alice to the side so we have room to see. Let's say Alice instantiates the counter by calling makeCounter, gives Bob access to the anchor method, gives Carol access to the decker method, nulls out her own Bob and Carol variables, but holds on to the counter. Having set this situation up, the only possibilities by which these 3 parties can interact from here is that Bob can count up and see the result, Carol can count down and see the result, and Alice can only do both. So this means even Alice is constrained by Alice's actions. So if Alice in the future becomes corrupted because some attacker took advantage of a vulnerability, if Alice has successfully gotten this far, then even the future corrupted Alice cannot escape from this constraint. This contains the central lesson of how practicing security with object capabilities differs from the security you're used to. With object capabilities, you express policy by the behavior of the objects that you provide. The make counter code combined with this code over here for instantiating and wiring things up expresses and enforces the policy corresponding to the prose that I just explained.
Just a point then. That means that now we can start building real secure systems, and the problem is that there are mistakes in the policy. So the problem is pushed to a higher level. You've solved
absolutely.
the problem at this low level, but now all the problems at the higher level still exist.
That's right.
Yeah.
That's right. That's until that's your main problem, right?
Yeah.
It's good news to find out
Yeah.
that your main problem is what should have been the real problem all along.
Yes. Okay.
Okay. So the next step in extending out onto the network is the one you saw diagrammed earlier, is how do you address objects on remote machines, but have this addressing of objects on remote machines be constrained according to an analog of the memory safety constraints that you've already seen, the unforgeable pointer constraints. So we wanted to stretch the reference graph cryptographically between machines, because most suspicion is suspicion not of code running on my machine, but suspicion of code running on other machines. So I'm going to show this with an enhanced secure EcmaScript, which is EcmaScript plus a promise library known as Q, plus a little bit of syntactic sugar, the infix bang syntax, that we've proposed for yet another future version of EcmaScript, but it's not present yet. All the functionality I'm talking about can be expressed without the syntax, but for expository purposes, I'm going to use the bang syntax. Okay, so let's start with the crypto. It's actually a very simple thing that enables it. The web has already done all the hard work by deploying TLS and the HTTPS URLs in order to create secure TLS conditions. So the analog of our object reference on the network is an unguessable HTTPS URL. And why is this? Why does this actually work in stretching the reference graph? Well, it's because of a strong analogy between the nature of unguessable secrets and the logic of object references. If you don't know an unguessable secret, you can only come to know it if someone else who already knows it tells it to you. Okay, so what about this mysterious bang operation? Well, you can write the bang everywhere that you can write the dot, and it means something analogous to the dot, sort of an enhanced dot. So what does dot mean? What dot mean, the way to think about dot is it's the do it now operator. Is Alice, by saying Bob.foo Carol, is saying I want Bob to do this request right now. There's a transfer of control from Alice to Bob. Bob runs to completion, returns some value to Alice, which Alice assigns to her result value. So Alice isn't even interested in continuing to do anything until Bob is completed. By contrast, yes?
So Bob could block forever, go to infinite loop to
That's right.
screw up Carol.
That's absolutely right.
So Carol is trusting Bob very
You mean Alice?
highly.
Alice is the one transferring
Oh,
control.
so Alice is trusting Bob very highly in this, yeah.
Yes, that's right.
Too much.
This is, the dot is just the conventional dot that we're used to from conventional imperative sequential single address space languages. And the single address space is that you can continue, even in Dr. Sess, to only be able to use the dot if Bob is local. By contrast, the bang means do it eventually. It means queue up the need to eventually ask Bob to do the foo request with Carol as an argument. And now Bob might be local or he might be remote. But no matter what, don't do it right now. You're queuing it for later. And since you're queuing it for later, what you do is right now you return a promise for what the result will be. There's also an analogous eventual property access that corresponds to the immediate property access. Since we're from here out through the remainder of the talk, we want to emphasize the distributed programming. We're only concerned about the bangs, and we're concerned about one further operation, which is the when, which is analogous to the try-catch, which registers for notification when this promise resolves. This is like the try block of a try-catch. This is like the catch block of a try-catch. They're just two functions provided as arguments. And if the promise resolves successfully because Bob's foo method completed returning a result, then the result, which is the resolution of this promise, becomes the result argument to that function call. And otherwise, if the promise is broken because Bob threw an exception, then the exception which broke the promise it gets passed over here to the function acting as the catch clause. When bringing this out onto the network, as I said, we want to abstract out over all of this variety of transport mechanisms, but the most important transport remains HTTP protocol over HTTPS connections. So on that transport, we map all of this onto RESTful HTTPS messages containing JSON payloads. The eventual send gets mapped to a post, identifying what method's being invoked, doing the JSON serialization of the arguments, and then when the result comes back, the JSON unserialization of the result becomes the resolution of the promise, and likewise with get. Get becomes get. And the when becomes just an abstraction over the means that browsers provide for obtaining, for getting notified when an HTTPS request completes. Okay. Now, my talk on Friday will go through, is going to take a very different cut through this example. My talk on Friday in the same room at 3 o'clock is sort of the successor of this talk. It will actually explain this example. But what I want to say today is simply that the code you see here uses nothing other than the elements that I've already introduced. The problem that this is solving is the creation of a secure cryptographic distributed money protocol where Alice, Bob, and the bank can be on 3 separate machines. And in the scenario that's diagrammed here, Alice wants to pay Bob money in exchange for some good that Bob would release to Alice. And the problem that we're focusing on is how does Bob know that he's been paid before deciding to release the good that Alice allegedly paid for. So this banking protocol has to solve all the traditional problems, prevent double spending, prevent forgery of currency, enforce conservation of currency, etc. This is realistically everything that Alice needs to say to engage in her part of the protocol. This is realistically everything Bob needs to say. So with all these problems solved, surely the code for the bank is where all the hard problems are taken care of. It must be terribly complex. Well, this is really everything that the bank needs to say in order to play its part of the protocol. This uses very little that you haven't seen in this talk. And by the time I get here, it uses nothing that you haven't seen in tomorrow's talk. It brings about a distributed cryptographic money protocol in collaboration with the code of Alice and Bob, despite the fact that none of those three pieces of code mentions any cryptographic concepts explicitly. Simply by by being concerned about the logic of money as a system of rights and rights transfer, and applying object design techniques to the expression of that as informed by object capabilities, what you do is you just end up writing this piece of code to express money, and the result is a distributed cryptographic money protocol.
Wait a minute. Don't believe you. What if the failure happens in the middle of this as a distributed system?
Okay.
Can you guarantee that your properties are conserved?
We can guarantee that the money is conserved.
With failure. So
With
if you have
failure.
distributed atomic operation.
No, we have local atomic operation. All of the
This
balances.
is distributed. This can be completely distributed.
Hold on. The three parties here are Alice, Bob, and the bank. All of the balances of each account is kept in the bank in these purse
So
objects.
the bank is doing the hard work.
The bank is doing the hard work. So these purse objects have a counter in them that is manipulated by this bank code. So this is the definition of purse. This is the balance variable. The balance variable is being incremented
So
with
if the
that.
purse object fails,
What do you mean purse object fails?
well, let's say the purse object is on another node. The bank is
No, the
distributed.
purse object, the bank itself is not distributed.
Ah, okay.
The bank,
It's a centralized
Okay.
system.
doing a system where doing money without a centralized issuer is a very interesting problem. It's a very,
Yeah,
very.
see, otherwise everyone would be already using
Right.
this
No,
on the
so,
internet.
so the term I would use for that is that would be a decentralized money protocol. That's a much harder problem. There's, by the way, very few solutions to it. Bitcoin is a fascinating approach to it. And Bitcoin is fascinating because it doesn't really solve the problem. It solves the problem in a softer fashion by using incentives on the various parties to approximately solve the problem and create a stable system where it's nobody's interest to violate the problem. But if they did violate it, the money would lose its integrity. So that would be completely not dealing with decentralized money, dealing with distributed money. Most distributed cryptographic money protocols have a centralized issuer, so I'm not cheating. Okay. Okay, good. Not all of my browser pages crash. So, to make distributed secure programming real, you can't just support the writing of the distributed programs. Programmers don't spend most of their time writing programs. They spend most of their time debugging programs. So there's another project called Causeway that has been working on instrumenting distributed programs and creating visualizations from the traces of what happened in the execution of the distributed program to help programmers debug distributed programs. Causeway has several visualizations. This visualization is called this oscilloscope. Each of these dots represents a different event. The red and blue different kinds of events. This oscilloscope is so named because it vertically organizes the events according to the position in the source code of the asynchronous operation that caused the events. And this oscilloscope this selection allows you to pick out, highlight things of likely interest as you're tracking down clues to try to pin down where the bug happened, where and when the bug happened.
So what do the lines mean? Do they flow control lines?
Okay. So yes, actually. So I'll actually take a moment to explain this. So as we know from Lamport's famous early paper, and likewise from Hewitt's paper at the same time that said the same thing that got almost completely ignored, we can think of distributed causality, Lamport's happen before relationship, as being the union of two orders, process order and message order. Message order is the order of, as messages flow back and forth, these asynchronous messages that go between processes, and the order of how receiving one message, doing things, and sending out other messages in response creates an ordering of things. Process order is the sequence of things that happens within an individual process. In the oscilloscope, the process order are all straight lines, the red and blue straight lines. The message order are these curved lines. And I'll stop there with the description. There's another visualization that Terry Stanley is working on called Causeway, called the causality grid. They're both parts of Causeway. In this case, the visualization is more directly organized in terms of process order and message order. The layout in particular is constrained by the interaction of those two words. And the outline on the left over here is a pure representation of message order and has synchronized selection of the visualization. And that's the causality grid at scale. At scale, you're not so much concerned about individual events, you're concerned about patterns over multiplicities of events, so that as you get used to what patterns your computation looks like when it's working, we're hoping, this is still speculative, that for some bugs you can spot them because you're seeing something other than the patterns you're used to seeing. It's completely speculative at this point. Okay. We're also bringing capabilities out through the user interface. The first breakthrough system was CACDESK by Mark Stiegler at Hewlett-Packard Laboratories, in which he realized that the basic capability concept that when Alice sends Bob a reference to Carol, Alice is both telling Bob what object she wants Bob to operate on, she's designating Bob, but she's also authorizing Bob at the same time. She's providing Bob the authorization. Mark Stiegler realized that our current user interface frameworks, for example, the open file dialog box, provide the same opportunity. These are mechanisms of designation, but by bringing the object capability perspective to it, we can reuse this mechanism of designation to provide the information needed to authorize things. So cap-edit, the editor that opened this dialog box, is asking the user to select the file for the editor to edit. The user does exactly the normal interaction, selects a file, and says essentially open. But as a result, cap-edit is not just told what file to edit, it's given the authority to edit that one file. It doesn't even know of the existence of any of the other files that appear here in this open file dialog box. There's the current research on this style of authorization by designation is a system we're working on at Google Research right now. Mark Lenzner, Arjun Guha, and Joe Politz have done a system called Delay. And over here we see two web applications. So this is now transposed into the web context. There's two web applications. And once again, the user playing Alice with this web application playing Carol and this web application playing Bob, by dragging this affordance over here and dropping it over there, the user is giving this web application access to the portion of this web application that it represents by that affordance.
So, can I ask a question?
So you can now ask, everybody can now ask as many questions as you want.
So I have one question on the user interface connection to OK capabilities. Is that people often make mistakes?
Actually, since you've asked so many questions, let me ask, does anybody who hasn't asked a question have a question? Okay.
So when you were discussing the eval in Caja, you
Yeah.
say, well, it has to obtain a certain subset, or must use the strict mode for synthetic checking. If you want to actually say, well, we have legacy code, third-party legacy code, is there a way to actually embed that into such a container
I'm
of
sorry,
Caja?
I missed part of it.
If you're using legacy code where you don't have jurisdictions on the eval string,
Right.
how do you deal with that?
So here's the, we do and do not deal with that. So let me explain what I mean by that. In the EcmaScript committee, when we designed strict mode, we designed it not, it cannot rationalize the scoping while being strictly upwards compatible from legacy JavaScript. And it's not. However, for much code and for almost all code that was written well, that follows JavaScript best practices, that code should be compatible with strict mode. And we've seen lots of code very painlessly ported to strict mode, but sometimes with manual intervention. So strict mode was not designed to be completely painless, where you can just accept legacy code automatically. It is designed to be sufficiently painless that for any body of code that's being actively maintained, the better scoping rules, the better error checking should be enough of an incentive that everyone should, from here on out, could use strict at the top of their program and gain benefits of those saner rules. And take the minor hit of development effort it takes to move over. SES imposes a further restriction, which is the freezing of the global variables and all the objects reachable from those variables, transit freezing. That's a restriction that we've relaxed. We've already relaxed it for Caja using the translator for legacy systems. And I have it as a to-do item for this quarter to do the same relaxation for the SES implemented on EcmaScript 5 without translation. I know how to do it. It's not something I've relaxed yet. Yes?
When you're thinking about static scope, it's not always statically scoped JavaScript. Can you give an example where it's not? Or is that
Okay. When you call foo, passing it this function, and foo says return x. Oh, I'm sorry. You need one more element to make this. So all of this is occurring in some nested scope. It's not occurring in a global scope. Nested scope, we have this variable x. Within this, we're calling foo with the function that results from evaluating this function expression. The body of the function refers to the variable x. When foo calls bar, what value do you think foo will receive in response? Well, in EcmaScript 5, the answer is 8. I'm sure you've all guessed by now what the answer is in EcmaScript 3. I will not explain why this is the answer in EcmaScript 3. It turns out that we were lucky in EcmaScript 3 days on this one, which is most browsers did not implement what was specified. Okay? But any conformant browser, Firefox was conformant. For any conformant browser, you would get gotcha. So in any browser in which you got 8, it was violating the EcmaScript 3 spec. Okay. Okay, Peter. I'm sorry, go ahead.
Can you elaborate again on how you made the DOM safe? Specifically, I'm interested how you basically make get parent safe
Okay.
without copying it or to copy it.
So we actually do not expose the DOM nodes themselves. When the containing page, the Caja, uses a library we've written called Domato, so our DOM taming library, which prefixed with DOM, and it also Domato is Spanish for taming. Caja, by the way, is Spanish for box, as in a lockbox for keeping money in. And it's also for capability of JavaScript. In any case, so our Domato library, when the containing page wants to hand to a given comment something that seems like a full working page with a document and a window and get parent and all that, the containing page uses Domato to create a system of wrappers around the subtree of the DOM. And it's those wrapper objects that are provided to the code in the comment. The behavior of those wrappers is behavior that we wrote, we wrote when we wrote Domato, and when you do get parent on that, it stops at the top of the virtual page, which corresponds to a subtree of the DOM. It doesn't allow you to ascend past that. Yes?
So when there are, let's say when bot is running, it is called by Alice, they still have an access to the document object, but the API through which the access to the document object is the Domato.
Well, sorry, if Alice is calling Bob, we're passing Carol, where Carol is a Domato wrapper, then Bob only receives the wrapper. And
So they still have access to the document object, but it's not the global one.
well, the wrapper has access to the document object. So Bob has access indirectly to the document object through the wrapper. But the only things he can do with the real document object are the things that the wrapper allows him to do.
They can do mutation
Yes, absolutely they can do mutation.
on the containing page.
Yes, but only mutation within that subtree. And they can only do mutation if what they've given is a wrapper. What they've been given is a wrapper that allows mutation. One of the operators that Domato provides is the ability to spawn a system of wrappers around subtree that's a read-only view. Domato does have the read-only, all the mechanisms for the read-only view. So anybody, it's not just the containing page that can wrap the real DOM with the read-only view. Anybody who has a read-write view, who wants to give somebody else a read-only view of the read-write that corresponds to the read-write view they have, can do so. So you can always downgrade the authority that you've got, and the read-only is a downgrading that we support out of the box. Okay, Peter.
Yeah, so what if I have a browser that I run locally, that I've sort of hacked up myself to go and look at all the internal data structures? So then this is all bypassing all this
That's right.
beautiful object capability security, right?
That's right.
So what do you do against that? There's nothing you can do against it.
What we
Except
do,
not send me any code and not let me execute anything.
no, what we do, so that's the wrong solution. What we do about that is, let's return to what this picture is showing. What we do about that is we arrange for patterns of cooperative interaction with minimized vulnerability to other parties to the interaction. So when I send you code, if you're in a machine, if I'm sending code to a machine that I'm suspicious of, then I should not depend on the behavior of that machine being according to the code that I sent. Okay? It's already a machine that I'm suspicious of, so it can do anything that it can do. The constraint is that if I'm transferring to you both code and some, let's say, remote references to other objects, that Well, you know, you're a machine that I don't trust, so you can do anything with references that you've been granted, these unguessable HTTPS URLs. However, any references that you have not been granted, you can't do anything. So your whole machine, as a single object, and taken in the aggregate, is one for which, when I send you code, the code is just data, as far as I'm concerned, that I'm advising you, here's a way that here's information to take into account with regard to how you might behave afterwards. But if you happen not to be malicious, here's what you should do with the code. Okay? But it's up to you whether you're malicious or not. I've already protected myself against the possibility
So
of your
the
malice.
critical information is not stored with me, it's somewhere else.
That's right.
Trust me with it.
And that's why these bank balances are not kept on Alice's machine.
Okay, then I have another small question, if I'm allowed
Okay.
to ask it. So what if I ask some botnet, pay a little bit of money, say just go around and sniff and give me some of these supposedly unguessable
Yeah.
guys, and then I collect a whole bunch of these references and I get all kinds of rights and
Absolutely.
nothing you can do about it.
Right. Well, I mean, so that's a wonderful service. Any URL that is discoverable in that manner is no longer secret. If
But you
you
don't know
have,
that.
well, so that's why services like this, that services that aren't quite like that, but that say, hey, did you really want to expose this, or ones that just sort of public search engines, which, you know, public search engines are just a marvelous thing. You can just, if you don't protect your, if you don't say, don't crawl my website, you say, go ahead and crawl my website. And then you can ask the search engine, okay, tell me all of the URLs that look like unguessable URLs. Well, if you see any, then you know that you're insecure. Okay? If you see any of the ones that you thought you were keeping secret, right? It should be impossible to find them by crawling. Okay?
Yeah,
It's up to you.
But that's not the point. These botnets might have all kinds of rootkits installed on all kinds of root systems,
okay.
and they're actually looking internally. They're not hurting anybody.
Okay,
They're
no,
just sniffing in all these virtual machines.
Right. Okay.
Uh,
Any secure system is built on a shaky assumption that the underlying platform on which it's running still has integrity, still operates the way it's supposed to. For what we're doing, that assumption is especially flaky because we're sitting on top of browsers on which people have installed plugins and extensions, sitting on top of legacy operating systems on which people have installed viruses, sitting on top of machines.
so what does one do?
Okay, so you've got to start somewhere. Okay? The people have tried the bottom-up approach, where we say, what we really are concerned about first is having really high confidence that we don't have any bugs beneath us. So let's build secure hardware, or let's build a secure microkernel operating system, and then just rebuild the whole thing from the ground up. Okay? And that's what I call, that's essentially what I mean by the backtracking approach. And those things have failed not technologically. Those are generally not technological failures. Those are failures to get resources and attention and adoption because you have to rebuild the world again.
Is that really true? Couldn't you use something like a TPM to guarantee that some piece of software is running without being tampered with? And then you wouldn't have to redo all that technology, right?
The answer is yes, you could use a TPM to verify for yourself that you're running on an insecure operating system.
Running on an untampered, output insecure operating system.
Well, I mean,
but untampered.
there's tampering and there's tampering. Okay? You can verify that the operating system kernel is still not modified. Okay? There are all sorts of avenues of attack that, this is a much longer discussion. They take it off.
Yeah, I don't want to.
The point here is that by starting with by starting at the attack surface, by which large organizations are, this is, you know, the web surface is the largest and most quickly growing attack surface that many organizations are presenting to the world. It's the one for which they're most hurting for lack of better security better security mechanisms, more flexible security policies, and by attaching this to a language which is being widely learned, you also get to communicate the message and you get people more aware of this as an alternate way of securing things. And the biggest thing that we lack is not an understanding of how to build the capability technology. The biggest thing we lack is an appreciation by the wider world that this is a technology we want to build. And I think this is the right strategic technology to build next to address that deficiency.
So I think we have foreseen a nice reception for you. If you have more questions, then Mark should just not drink wine with these things over to give you a technical answer. So I propose that we thank Mark for being here. Thank you. There's one more of this tomorrow.